In this video, I'm going to walk you through the process of downloading articles retrieved from Web of Science or Scopus and conducting a clustering analysis to group the articles based on the similarity of their abstracts. Ideally, you would use the full text for clustering analysis. However, this requires a powerful graphics card and a large amount of memory to process the extensive text data. As a result, abstracts are commonly used for this type of analysis, even in published research studies. The first step is to download data from Web of Science. Instructions for Scopus will be introduced later. In a screenshot, I searched for collaborative problem-based learning as the topic and limited the results to journal articles. This search returned 338 articles. To export the data, click on Export, then select Export Excel as the export format. In the pop-up window, select all records from 1 to 338. Under Record Content, choose Full Record. Then, click the Export button to download the dataset. Open the downloaded file in Excel. You will see the full record format, which includes a lot of article information. For this assignment, we only need the article title, abstract, and publication year. Therefore, keep the article title, abstract, and publication year. Additionally, add an ID column to number the articles in the dataset. Remove all other columns to prepare the data for further analysis. Please save the process file in the original XLS format. This screenshot shows how to download search results on Scopus. I searched with the same conditions and obtained 1,333 articles. To export the data, click on Export, then select Export CSV as the export format. In the export settings, select articles 1 to 1,333. Additionally, check the boxes for document title, year, and abstract. Then click the Export button to download the dataset. Open the downloaded CSV file in Excel. Add an ID column to number the articles in the dataset. Additionally, remove the link column from the dataset. Save the process file in the original CSV format. Now it is time to run clustering analysis in Orange. Make sure you download Orange and installed text mining add-ons for this assignment. If you don't know how to download or install add-ons, please check the tutorial videos in the first module. For Windows users, if you prefer not to install Orange, you can download the standalone version. Simply unzip the file and run the Orange application. Orange uses a graphical interface for all analytical and data processing functions, so you don't need to write any code. Instead, you will construct analytic flows using visual components. Please note that Orange automatically executes all analytical widgets once they are connected within the flow. The screenshot shows the analytic flow for this assignment. This flow imports your process dataset, processes the text data for analysis, encodes the text using a basic TF-IDF approach, computes distances among articles, and performs hierarchical clustering. I have also included various widgets, such as a word cloud and keyword extraction, to help examine the clustering results. Finally, you can export the clustering results for further examination. The first step is to add the file widget to your analytic flow. Double-click the file widget to open its settings. Click the folder icon to select the file you extracted from either the Web of Science or Scopus database. Please note that the Web of Science exports data in XLS format, while Scopus exports data in CSV format. Both formats are compatible with Orange, so you only need to select the file you want to import. Orange will automatically detect the file type. In the screenshot, you can see that my data file has been successfully imported into Orange with 4 columns: ID, publication year, article title, and abstract. Connect the corpus widget with the file widget. Because we will group articles by abstract similarity, drag abstract under used text features and article title to the ignored text features. Add the pre-processed text widget to your analytic flow. This widget provides a range of options designed to reduce noise in your dataset. For example, a word with a capitalized first letter may be treated as different from the same word in lowercase. To reduce such inconsistencies, you can convert all words to lowercase. Of course, you might have a different perspective. For instance, all uppercase words can sometimes carry special meaning. In the next module, we'll introduce a more advanced technique called word embedding, which is a mainstream method in modern text analytics, including its use in large language models. That said, this does not mean the traditional TF-IDF approach is ineffective. In fact, TF-IDF can work very well, especially when the collection of articles centers around unique research directions within collaborative problem-based learning. The assumption is that each research direction uses unique terms more frequently than others. TF-IDF identifies these frequently unique used terms and assigns them higher weights, allowing clustering analysis to group articles by their thematic focus. Additionally, stop words, common words such as articles, prepositions, and conjunctions, are typically removed during pre-processing. These words occur frequently, but contribute little to the core meaning of a document. Eliminating them helps improve the quality and accuracy of your text analytics. Add bag of words to the analytic flow. Bag of words is the traditional TF-IDF approach in text analysis. Again, it still can work very well in article classification. Keep the default settings as shown in the screenshot. In text analytics, cosine distance is one of the most commonly used measures for calculating the semantic distance between text samples. It helps determine how similar two pieces of text are by measuring the angle between their vector representations, rather than comparing raw values. This approach is especially effective when using TF-IDF vectors, as it emphasizes word usage patterns rather than text length or absolute word counts. In all tutorial videos in this course, I aim to explain these technical concepts in an easy-to-understand format. However, if you're interested in exploring the technical aspects further, please post your questions on the discussion board. I'll be happy to provide additional explanations based on your inquiries. Add the hierarchical clustering widget to the analytic flow. This method groups similar texts based on content similarity. In the screenshot, the results are displayed as a tree structure because the bottom-up approach begins with each document as its own cluster, then merges the closest pairs one at a time. This process continues until all documents are combined into a single, large cluster. If no pruning is applied, the result will be a large and complex tree. To simplify the output, please limit the maximum tree depth to 3 layers. This will produce 4 clusters, as shown in the screenshot. To further analyze the results, select one of the clusters. In the screenshot, I selected the cluster indicated by the arrow. The action will allow me to explore the contents within that cluster with other widgets. Add the Corpus Viewer widget to the analytic flow. This widget allows you to examine individual articles within the same cluster. The cluster I selected in the hierarchical clustering widget contains 52 articles, which can now be reviewed in detail using the Corpus Viewer. Add word cloud to the analytic flow. A word cloud is a visual representation of the most frequent words in your dataset. In the word cloud, larger words appear more often in your text data, while smaller words appear less frequently. The most meaningful approach is to generate word clouds for all 4 clusters. Compare key terms which only shows in one cluster, but not in the rest of clusters. These keywords often represent unique key themes or topics discussed in the selected cluster. Most of you should see the word cloud results immediately after connecting the widget to your analytic flow. If you don't see any results, try double-clicking the connection line to edit the link. Make sure the connection is set to transmit selected data to Corpus. This ensures the text data is properly passed into the word cloud widget. Add the Extract Keywords widget to your analytic flow. Again, we use words of bag widget or so-called TF-IDF, which stands for term frequency, inverse document frequency. It's a common technique in text mining used to measure how important a word is in a specific article compared to all the articles in your dataset. TF-IDF highlights unique and meaningful words by giving them higher weights. For example, My Web of Science search focuses on journal articles in collaborative problem-based learning, PBL. After dividing the collection into 4 clusters, I examined the keyword results for one selected cluster. The top keywords identified were PBL, skills, course, and perceived, indicating that this cluster likely contains articles exploring the use of PBL to develop problem-solving skills and examine participants' perceptions of the learning experience. I can return to the corpus viewer to validate my observations by reviewing individual articles within the same cluster. It appears that my interpretation is on the right track. Many of the articles in this cluster focus on measuring problem-solving skills and often explore participants' perceptions. Additionally, this type of research seems to attract significant interest from scholars in the field of medical education. Again, most of you should see the extract keyword results immediately after connecting the widget to your analytic flow. If you don't see any results, try double-clicking the connection line to edit the link. Make sure the connection is set to transmit selected data to corpus. This ensures the text data is properly passed into the extract keywords widget. You can go back to the hierarchical clustering widget and select and interpret another cluster. In extract keywords widget, the top 5 keywords are PBL, group, knowledge, face, and online. Then, when I returned to the corpus viewer, I found that many studies aim to analyze group interactions during the problem-based learning process. Finally, you can export the clustering results for further analysis in Excel. To do this, connect the Select Columns widget to your analytic flow. Since the extracted textual features are not the focus of our export, move those features to the Ignored panel, as shown in the screenshot. Then, move ID and Cluster to the Features panel, and place article title and abstract in the Meta panel. Connect the Save Data widget to your analytic flow. Double-click the widget, then click the Save As button. Assign a file name and select Microsoft Excel Spreadsheet as the export file format. This concludes the tutorial video. If you have any further questions, feel free to post them on the discussion board. I will introduce another clustering approach in the next module. Thank you for watching the video.